In our last video, we looked at a function much like the one I have graphed here and found all of its local and absolute extrema. For this function, it has an absolute minimum at a and an absolute maximum at x3. It has a local max at x1 and then local mins at x2 and b. The first derivative test for local extreme values says if f of x has a local minimum or a local maximum at an interior point c of its domain and f prime of c exists, then f prime of c is 0. So I'm only looking for local mins or maxes on the inside at an interior point, so I need to leave out a and b. And so that gives me 1, 2, 3 local mins or maxes to look at. And I know what you're saying, that this is an absolute max. But it also meets the definition of a local max. If I take an open interval around x3, that is the highest point. One way to think about an absolute min or max is that it is also a local min or max that's just bigger than all the other local minimums or maximums. So really on the inside I'm looking for any min or any max because all of my absolute mins and maxes are also very special local mins and maxes. And this theorem says if I have a local min or a max at an interior point and the derivative exists, then the derivative has to be 0. 3 spots to look at. This is a cusp, so the derivative does not exist. At these 2 spots, it does look like I have a horizontal tangent line, a line with a slope of 0. So it does seem to match my description. This theorem tells me that if I have a local min or a max and a first derivative that exists, I have to have that horizontal tangent line. My turning points will have those slopes of 0. And if I put that together with the fact that that was a cusp, it tells me where to look on the inside for mins and maxes. That I need to either be looking for places where the first derivative is 0 or places where the first derivative does not exist. And that brings us to the definition of a critical point. An interior point of the domain of a function where f prime is either 0 or does not exist. A critical point is always an interior point and is a spot where I either have a slope of 0 or where the first derivative does not exist. So for this function, my critical points are x1, x2, and x3. Because at x1 and x2, I have horizontal tangent lines where my first derivative is 0, and at x3, my first derivative does not exist. Okay, critical points, places where my first derivative is 0 or where the first derivative does not exist, these really become the places where I might have mins or maxes, my local mins or maxes, and this brings us to a procedure for how to find absolute mins and maxes for continuous functions over a closed interval. All right, so how to find an absolute extreme value of a continuous function over a finite closed interval. Step 1, find all of the critical points. So in this step, we'll need to take a derivative. And then we're going to look for anywhere where that derivative is equal to 0 or where it does not exist. Step 2, evaluate the function at the critical points and at each endpoint. What that will do is give us a list of y values. And in fact, looking at this graph, it would tell me all of these y values, each endpoint, and then each one on the inside where my derivative was either 0 or does not exist. Well, if I think about that, that's just a list of numbers. And the biggest one will be my absolute max, and the smallest one will be my absolute min. So all we have to do is write down the largest and smallest of these values. And we'll have found our absolute max and absolute min. Now, this procedure works for continuous functions over finite closed intervals because that's where the extreme value theorem guarantees us that we will have an absolute min and an absolute max.